Now that we know how to take derivatives, we're going to look at one of the big applications, or at least one of the first big applications of differentiation, which would be the idea of optimization, meaning finding the best for a certain situation. So if you're working with a profit function, the best would be a maximum profit. If you were working with a cost function, the best point on the graph would be a minimum. So we're looking at maximum and minimum problems. Back in your algebra courses, if you had a quadratic function, you had a vertex formula. But in general, something like this first graph here, if I want to find this particular point here, or this point, or this point, there is no formula. Okay, what we'll have to do is use calculus. So since we know how to take derivatives, we're at least in a good place. We've done the setup for almost everything in this chapter already. I've had you look for these points without even really acknowledging it. We've been looking for places where tangent lines were horizontal. That's exactly your first step for max-min problems. And that's usually the hardest step. It'll be the algebra, not the calculus. I want to use these two graphs just to identify the interesting points on the graph. I find that looking at like the definitions that are at the bottom of this page, it's just a bunch of symbols and words, and I think sometimes if you have a picture to look at, then the words and symbols will make a little more sense. But mostly I just want you to have pictures in your head so that you know exactly what you're after. So I'm just going to label the important points on both these graphs with what they're called so that you have some idea. So this first point here we refer to as an absolute maximum, because it is absolutely the highest point on the graph. Okay, it's got a larger y value than any other value on the graph. We also changed direction there, so it looks similar to this point. Okay, they both have the similar behavior. We're going from increasing to decreasing. So when we're actually doing problems, these will both, at least blindly without a graph, they'll both look like maximums. So we'll want to be able to tell the difference, the type they are, and so on. This one we refer to as a relative maximum. So it's not the absolute maximum, but there is this behavior that on a small interval, meaning relative to this interval, that's the highest point on the graph. Relative to the entire domain, then we have our absolute maximum. This is where things get a little confusing. Based on what I just told you here, if you looked at this interval, then that would be the highest point relative to this interval. So this is also a relative maximum. Generally, we'd prefer to use the word absolute because it's a much stronger word, but these both have the same behavior. So they're both referred to as relative maximums. What that means is we change direction there. We go from increasing to decreasing. So that on a small enough interval, they would be the highest points. Okay? But mostly think of the feature of going from increasing to decreasing. And what happens in between is where the slope is 0. That's why we've been doing that type of algebra problem, taking a derivative and setting it equal to 0. That'll be our first step. The rest of it will be pretty easy. So these are both relative maximums or maxima. This one is absolute. Okay, so what would be a good name for this point here? Well, here we go from decreasing to increasing. So relative to an interval here, that would be a low point. So this is referred to as a relative minimum. Is it the absolute minimum? Definitely not. There are points far below that point. We just change, it is just a valley. It's a low point on this interval. And for this graph, there is no absolute minimum, because those arrows indicate the function goes downwards forever. Okay. So that's the idea with these. We have relative max and mins. And if one of them happens to be bigger or smaller than all the other points on the graph, then we refer to it as absolute. Just to confuse you even more, you'll see down below with absolute, sometimes, and it'll vary book to book, author to author, but the word global could be used interchangeably with absolute. Absolute means over the entire domain. That's what global basically says. Relative could be interchanged with the word local. Global and local clearly go together. They sound similar, absolute and relative similarly. I prefer to mix them and use local and absolute. So in the videos, just make sure you understand. Relative and local are the same. Relative to an interval, local to an interval. Absolute and global are over your entire domain. I think that's almost all the terminology just in this one graph. Let's look at this other one here. I'll change colors here. So now we should be able to look at this and say a few things. This point here certainly is above every other point. So absolute maximum. It's not relative. And that also can confuse people. Over here, I describe relative behavior as going from increasing to decreasing or decreasing to increasing. Notice over here, there's nothing to the right of this point. So you can't really say if it's decreasing after. You have to, for a relative max or min, be able to put an interval around it. And there's nothing to the right. So endpoints of a graph can at best be absolute max or mins. There's no change in direction there, and that's what we generally are referring to by relative. So what about all these others? This and this, these would be referred to as relative max. This one, and this one would all be relative minima, because we change from decreasing to increasing in each one of these. This one with a point here, the sharp part, is a kind of a troublemaker for us, but it does satisfy the conditions that they're all three low points. Now, one of them in particular is an absolute minimum as well. Okay, so this graph has both absolute max and absolute min. And the reason is there are no breaks in the graph, and we chop the graph off. We give it endpoints, so it can't go forever up or forever down. If we had a vertical asymptote or something, that would be a possibility. So the idea of continuity is what gives that to us. So all three of these are relative. This one is also the absolute lowest point on the curve. So I think if, based on these pictures, it's a little bit of a mess. It looks cleaner in the annotated notes. But I'm talking through this, so imagine my hands waving and stuff. Since you can't see that, you're seeing arrows all over the place. So hopefully that kind of makes a little bit of sense. And if you scroll down and now try to match the definitions up, they might make a little more sense, at least for absolute max and min. You have an absolute minimum at some value C if the functional value is less than every other value, or equal to. You have an absolute maximum if you're greater than every other value. Okay. And then the relative is kind of the same idea, except you're looking at just over a particular interval. So local and relative go together, global and absolute. And I for some reason, I'm likely to use local with absolute, which kind of mixes the two analogs, or I don't know, synonyms, something like that. But for some reason, I never use global. I think probably my calculus book used absolute and local, just one of those weird things. So it just kind of went from there. So don't get too hung up on the phrasing here. If you have the pictures in your head of what these points look like, then you have the definitions. Okay. So what we're going to be interested in doing is finding these. So if I'm interested in looking for points like this, at least these four, notice that the slope of the tangent line is 0 at each of those. This is a problem because the slope's not 0 there, but it's a relative minimum. But you might notice that the slope looks like it's maybe vertical. So these points will be found by either places where the derivative is 0 or undefined. We're mostly going to be concerned with points like this. Okay. So that's kind of the setup. Now we're ready to really just tie together things that you saw in Chapter 2. You've done all the bits and pieces. We just haven't really given everything names. Now we have. And then just put the pieces together. But you've done most of the tough work, which is taking a derivative, setting it equals 0, and solving. You just didn't know why you were doing it. This chapter will sort that out. Okay, on to the next page.